So we started talking about uninformed search. Let me just refresh your memories. The idea there is that we are talking about intelligence, and we are saying one of the ways in which intelligence can be manifested or can be demonstrated is by doing some complex problem solving. So we said, okay, let us sub-goal on problem solving. What are the various methods by which we can solve a standard problem or any problem or general problems? What's the general purpose problem solver? And the paradigm that AI community has been working on forever, for the last 40-50 years, and it's a very generic paradigm, and this paradigm applies to pretty much every problem that you can think of. It's called search. So that's what we started working on, and this is a first formal definition of search. The input in this definition is a set of states. However, those states are not explicitly, the graph is not explicitly represented. So you know that there are a set of states, and there is an operator, and that operator, if you apply that operator on a state, or on any of the operators, then you get to a new state. But this description is not provided to you in an explicit graph. This description is provided to you in code somewhere, in some sort of an abstract form. And so you have the capability of generating states by starting from some start state, which is given to you, and then applying the various operators and getting to the various other states that you can reach. And you have to reach some place, right? That's the point of problem solving. You want to reach a goal. A goal can be a single state or could be a set of states. In this particular case, you are given a test. So you can check for any new state you visit. You can ask your code, is this a goal state? If your black box domain descriptor says yes, it's a goal state, that is where you are done. And so this is the first way of starting to solve a problem. And the question is that what is my path that takes me, what is the sequence of operators, what is my path that takes me from the start state to any state that satisfies a goal state. And if you want to consider the optimization version of it, then you want to find the shortest path. And this is essentially a shortest path problem. So some of you must ask me, why is Dijkstra not a good enough algorithm? And anybody has an answer? Yes? Riley.
I'd say limits of memory.
Because Dijkstra assumes that I can do operations on the whole graph. Whereas we have changed this model slightly. We have said that you can generate the whole graph if you wanted to, but you'll probably never want to because it will be too huge to store in the memory. So therefore you only want to generate the part of the graph that is absolutely essential for you to reach the goal state. And we started with this particular puzzle, the 8 puzzle. Many of you had not seen it because you have seen the 15 puzzle. That was the joke last time. So you have a start state and you want to get to this goal state. And so in this particular case, there is exactly one goal state. Because, that doesn't have to be in general. And so what are my states, right? So my state description is any configuration. My actions are, I can think of 4 actions: move blank up, move blank down, move blank left, move blank right. And based on which action I can take, I get to different states. And we can assume that each action costs 1, and the goal test is whether I am in this particular state. So this is the standard. You can formulate the original 8 puzzle problem into a search problem. So we started discussing various search strategies. The first question was, how would we evaluate the search strategies? And these are the criteria. Completeness, does it always find a solution when there exists one? Time complexity, space complexity, optimality, systematicity. Systematicity is, does it visit each state only once or visits a state more than once? And then to define the time complexity and space complexity, we define 3 parameters, B, D, and M. This is just quick recap. B is the maximum branching factor of the search tree. D is the depth of where a solution exists, the least depth where the goal exists. And M is the maximum depth of the whole search space, and this depth can be infinite. So we discussed 2 techniques last time. One was breadth first search, one was depth first search. This is pretty much old news for most of you, or all of you hopefully. So breadth first search started by first generating this node, or this is depth first search, then going down into some path up to the very end, and then backtracking to the parent and other children, so siblings, and then going and searching the rest of the tree. Okay, and at some point I will find the goal. This is also called chronological backtracking, if you care. It's backtracking because at some point it is going back, and it is chronological because it is going back in the order it came. And this term will probably come up again. Okay, it's not complete. Again, this is recap. It's not complete because if my M, which is the search depth, is infinite, then my goal could sit here, but I may be in that infinite subtree here and will never come back. So therefore it's not complete. Time complexity is b to the m because in the worst case I may have to expand up to the maximum depth, which is pretty bad. However, space complexity is pretty cool. Space complexity is only b times m because I only have to maintain the history of how I came to this point, so that when I backtrack, I take the other. So we discussed that last time. And then we discussed breadth first search, and the breadth first search, the idea was that we are going to expand level wise, depth wise. So first A, and then we'll expand all nodes up to depth 1, so B and C. Then we are going to expand from this frontier all nodes up to the next depth, so D, E, F, G, and H, and so on. This is complete because as long as B is not infinite, B is usually not infinite, but it can be. Especially if you're doing control problems, and BJ is an expected control problem. So if you have any questions about really complicated continuous variable problems, ask him. You have a question.
My name is Somesh.
Somesh.
So can we not apply the similar criteria to depth first search, saying if it is not, like we said, depth first search is not complete.
If M is infinite, it's not.
Right. We said here it's complete. So we can say that DFS is complete.
DFS is complete if M is finite. There will be problems with repeated nodes, so we'll just get into that towards the end of this lecture, and so that will make it clear. Time complexity B to the D, so we don't have to search up to depth M because we are searching in depths. So as soon as we find the goal, we don't have to search further, and so we only have to expand B to the D nodes. Space complexity again B to the D because you have to keep all the nodes in the memory. And then there was a question last time, we had some confusion whether we would only maintain the frontier, which is the last layer, or the whole tree. Okay. So how many of you feel that we should only maintain the frontier, the last depth from which we have to expand? How many of you feel that that would be sufficient? Okay, how many of you feel that we have to maintain the whole of the subtree that we have explored so far in the memory? Okay, so it suggests that about 80% of the class does not feel anything. Yes?
You could just maintain the bottom two layers so you know where not to go back to, and then just go on from
So
there.
if you maintain the bottom two layers, then what happens? Sorry.
As you expand a node, at least you know that you don't want to go backwards. The advantage is that there's less space.
Good
The disadvantage
question.
you don't.
So let's not talk about repeated nodes. We will discuss repeated nodes very soon. But there's another reason why we need to maintain the whole of the search tree. Yes, Zan, right?
Yeah.
Yes.
So with the whole, that gives you the history, so you know exactly what was the path that was taken.
Yeah.
to
So
get
your final the goal of the problem is to get the path. So if I only have the frontier and I reach the goal, yes, I found the goal. How did I come here? I have no idea. So the only thing I know is just one layer older node of how do I get it. Right? Now, there is a time-space trade-off happening here. So if that space you want to avoid, then what people do is that they maintain two depths. One is at d by 2, some depth k that you are expanding, and one is k over 2. Okay, and so that's some kind of a divide and conquer that happens. And so as soon as you find the goal, you sort of figure out that which node took you to the goal, and so you keep dividing. Again, I'm not getting into this. It's interesting, but out of the scope of this discussion, as far as we are concerned, we are going to maintain all of these in the search tree in memory, and therefore it will be about b to the d plus 1 or something. And yes, it is optimal only if your step cost is 1. Because if your edges have costs, like this has cost 1 and this has cost 10, then I'm exploring this in a very weird cost framework. So if you have costs, then the equivalent algorithm, which is not too far away, is called uniform cost search. And again, we discussed this. The idea is that we are going to expand cost-wise as opposed to depth-wise. We will have a frontier, and all of those frontier nodes will have cost up to a certain point. So initially we will expand this one because this cost is 1, then we will expand this because the cost is 3, then we will expand this because the cost is 5, then we will expand this because the cost is 6, we will expand this because the cost is 7, and then 8, and then 9. And that's called uniform cost search. Property is very similar to breadth first search, except that the time complexity now does not depend on the depth of the goal, it depends on this quantity C over E. So E is the minimum cost and C is the total cost up to the goal. And so your minimum increment now does not become the D, it becomes C over E. And you can think about it, it's not terribly complicated. So we were here last time. Let's move forward. Now we have discussed two algorithms, really two kinds of algorithms. One is very little memory, go zoop and never come back potentially. Or maybe really do a lot of exploration somewhere down deep in the tree and then finally comes back and gets to the goal. That is depth first search. The other we have discussed is slowly keep increasing my depth or keep increasing my cost and eventually reach the goal. Right? This has a balance between memory and time. This has bad time, very good memory. But this balance also is exponential in breadth first search. So bottom line is that time and memory, there is a continuum, and I'm not talking about really theory of relativity or anything like that. In reality, space and time are not really that equivalent. And the reason is that I can run for my machine for another day, but in order to get memory, I will have to buy RAM or buy disks. So they are not really equivalent. So if my memory is exponential, I mean time is exponential is also bad if it goes into years obviously, but if my memory is exponential then it just life becomes completely messed up. So for example, if I have a simple 2 GHz CPU, this is probably 8 years old slide, so 1 GB main memory, which is obviously no longer true, now you have much better, but because this is exponential you can say that okay, we can solve problems with one more state variable or something because these are all exponential problems. And if I'm expanding 100 instructions per expansion, each node takes about 5 bytes, then I can do about 200,000 expansions per second, which means that my memory is filled in less than 2 minutes. And this doesn't mean, the point is, exponential memory sucks. It's really bad. We cannot afford to have an algorithm which has that bad memory characteristics. So really what we want is somehow maybe the time complexity of breadth first search, but the space complexity of depth first search. And obviously there is no magic, right? So how do we get to that algorithm? So is everybody okay with the problem that we want to solve? So that is our goal. We want to come up with an algorithm that has really, really awesome space characteristics and good, decent time characteristics. Okay. So the first idea is the following. You are doing breadth first search, let's forget uniform cost and breadth first search are really the same thing, practically. So you're doing breadth first search, and at some point your memory is filled. What can you do? What's the first thing that comes to your mind?
Free the memory.
Sorry?
Free the memory.
Free the memory. So if you have to expand more nodes, well, too bad, I'll just get rid of some of the really bad looking nodes and throw them out. And keep expanding. That's called beam search. It's called beam because there's a beam. That is the maximum memory I'm allowed. And as soon as the beam gets filled up, some really old node goes out the window. And so I only keep this beam in memory. But I keep expanding my frontiers. What is an obvious problem with this approach?
You might miss the solution.
Is this complete?
No.
How many of you feel it is complete? How many of you feel it is not complete? Okay. So this is beam search. It is still used. You know, you will be surprised. Lots of people use beam search in practice. Practice and theory, you know, they often go together, but sometimes they don't. This is the interesting algorithm that we will learn in this part of the talk. Or
So
class.
in beam search there can't be false negatives. So if it found a hit,
If you find a goal, then you are through. Always. That's true always. Yes. Ryan.
Yeah.
Yes.
So how do you prove the worst node if you don't have a heuristic?
Yeah. So that's a good question. And I was putting it under the line. We can come back to it in the next section. That's the right question to ask. Okay, so the algorithm that I want you to learn in the first 1/3 of the class is iterative deepening search. Okay? Now just give me a quick heads up. How many of you know about iterative deepening search? Okay, so you guys can sleep for the meantime. I would suggest that you do not answer questions so that, or I mean, you can think along, but you know, I'm teaching this to the rest of you. So the idea is the following. Suppose somebody told you, you know, this really rich man who knows everything, or God came along and told you, you know, the goal lies at depth 10. Which algorithm would you use? Depth first search. Exactly. Why? Because you know, and in fact, not depth first search. Actually, that's not the right answer. Depth 10 search. Exactly. You will use depth first search, but never go beyond depth 10. Because you know that God told you that the goal can be found within depth 10. Right? That's called depth limited search. Okay? Just a name. We like to coin names, right? If you don't coin names, then you know the research people outside the research community. I mean, people outside the research community need to feel that researchers do something. so we coin names for simple ideas. That's called depth limited search. Now, suppose of course, you know, the standard problem is where does God come from, right? And you know, people have been trying to find the answer to that question forever. So I don't think AI can solve that problem. So we don't know what that depth is, but what can we do about it? Okay, we can guess. Suppose we have no other information about the world. We only have a black box that is telling us, you know, successors and goal tests. What is a dumb way to guess? Yes, Siege.
Thank you.
Yes.
How much memory we have? So if we know how big a node is, we kind of figure out how much we can cram in our memory.
That's a very good point. Tell me, do you understand depth limited search?
I read it, doesn't mean I understood.
What is the memory requirement of depth limited search? Sorry? B to the D? How many of them?
B times the limit.
Okay, think about this. It's okay, it's fine. We are learning this together. So, we're talking about depth limited search. It's very similar to depth first search. Depth first search, what is the only good thing about depth first search? Memory. Right? It's going to take pretty much linear or non-exponential memory. Right? B times the depth that I'm going to search, which in depth first search was M, but in depth limited search will be the depth bound that I'm given. Right? So we have a lot of memory at our disposal. Unless B is a million or something. You know, B is never that. Otherwise it's not. So that is not the answer. There's another answer. Zen.
You could start off with like a small number and just like if you don't find anything, get bigger and bigger and bigger.
Okay. That is called iterative deepening search. And can you actually connect it with what Zan said and the name? You are iteratively deepening your search.
So would it be a case of you just start from the root and say, okay, if not the root, Or are you gonna try to do something more and like, okay, do like 50% of what the max depth of the tree is, and then.
You don't know max depth of the tree. All of those things are not known to you. No other heuristics, no other knowledge. What's your name again?
My name's Tarek.
Tarek.
Sorry, this is kind of a naive question, but isn't that almost like breadth first search? If you're looking at depth 0, you go that many nodes. Or depth 1, you look at all the nodes at depth 1.
Can somebody respond to Tarek? What's the difference?
You're not keeping them all in memory.
I guess you know it didn't work out at that one, you discard it. Okay.
So discard and restart.
So all the memory requirements is still linear, or b times the depth. It's not b to the raised to the depth. And that is all the exercise that we are trying to accomplish. We want to reduce our memory footprint. There's not much we can do in terms of time, unfortunately.
So you're going to repeat.
Yeah. So your name?
My name is Samim. You're going to repeat
Samim.
some of them.
Right. You're going to repeat some of the nodes. And that's going to be, that overhead can be really bad. So it's not clear whether this is a win yet. You have a question?
Well, yeah, this is kind of backing up.
What's your name again?
Sorry, my name's Tyson.
Tyson?
Tyson, yeah.
Tyson, okay.
Maybe dumb question, but something I didn't understand. When you say it's b to the depth or b to the limit, you like in a recursive implementation or using a stack, you only have like one vector in memory at a time. So why is it b to the m and not just m?
So it's b times the limit. Let me run you through the algorithm. Maybe we should discuss this once I show you the algorithm.
Okay.
I'm not sure where you guys are confused, but this is the simple idea. We start with depth 0 and keep increasing the depth and do a depth limited search up to that point. And if we find the goal, we are done. If we do not find the goal, we keep increasing this. So this is the algorithm. Let me show you the implementation. So when the limit is 0, I'm going to start with the initial state, not expanding anything, useless, waste of time. Let's start with limit 1. What happens? Well, I go here, start here, go to this point, don't find the goal, come back, go to this point, don't find the goal, go back, I'm done. This is the only search I'm going to do. At limit 2, this is the search I'm going to do. At limit 3, this is the search I'm going to do. Start here, go here, come down, chronologically backtrack. So visit this part of the subtree, come back, visit this part of the subtree, eventually come back, come to this part of the subtree, and so. Okay. It's important to know that the algorithm memory that I am storing, I am only storing the history of how I came here. So at this point, what I will remember is that I came from A and C, and of C I am the first child of A, C is the second child, or something like that. So in other words, at A, this part is explored, this is not explored. At C, this I am exploring and this is not explored. So I am not going to store the whole subtree, I am only going to store the path to this point and all the children of all the nodes of my ancestors of whether I have explored or not explored. This is same for depth first search. So my memory footprint is b times the limit. Now the question we have to ask is, what is my time overhead? So are you guys okay with the memory footprint? Do you see that if this algorithm works, then the memory is going to be really low? Because if that is not clear, then we are stuck somewhere.
Like in the top right scenario, which is what you're just saying, like in a recursive implementation, you wouldn't have to keep track of where you've been. It would just, like, iteratively, you would visit each node in your for, and so it would just be M, right?
So you have to maintain the stack.
Yeah, but you can implement depth first search without using a stack, right? If you just use, well, I guess the stack is implemented for you if you use
That's
recursive.
same
So
thing, yeah, it's the same thing.
Yeah, okay, I get it. Yeah, got it.
So you're maintaining a linear or sort of two product of the linear, basically. So everybody with me? Okay. So now the real question is, how bad is it in terms of time? Because if it is not too bad, then I think we've got a all right. what is the number of nodes generated if I search up to depth L in a depth limited search?
Generate. I mean, visited. B to the L.
B to the L.
Alright, most.
B to the L, that's all right. Doesn't matter. Why? 1 plus D plus B square, right? Because every child can have further B children. So B times B square plus B cube plus up to B to the L, which is geometric series B to the L plus 1 minus 1 over B minus 1. Yeah, B to the L. You're right. Sorry. What's your name?
Paul.
Paul. So B to the L. Everybody with me? Now, up to depth L, if we found the goal at depth D, how many depth limited searches would we have done in iterative deepening search?
Log B.
How many depth limited searches will we have to do in order to find a goal at depth D?
D.
Yes. In the first depth limited search, the number of nodes we expanded is 1. In this, okay. So now you can see basically. So this is the number of nodes that we have to generate in depth limited search. This first node is going to be expanded how many times?
D plus 1.
D times, right? Or D plus 1 times, whatever, 0 if you are starting with depth 0. This next layer is going to be expanded D times. It will not be expanded in the 0th DLS, but it's going to be expanded in all others. And this really, the last depth is going to be expanded only once. So the number of nodes generated in iterative deepening search is this. Do you know how to sum this? This is called an arithmetical geometric progression, AGP. Not very hard to sum. Actually, you can take that as an exercise if you care. Okay. Interestingly, the ratio of this quantity over the number of nodes generated by breadth first search, which is B to the D or something, is actually B plus 1 over B minus 1. That's the overhead. When will this ratio be really bad? When B is 1.
We can't do 1.
That will mean that it's a path. Think about it, what happens when it's a path and you are slowly increasing depth. You're doing linear versus linear.
Yeah, we don't like the equals 1 numbers. We don't like to divide by 0.
Yeah, so that's why that is why it will be really bad. So now let's see how bad this is, right? This is the ratio of iterative deepening depth first search to breadth first search. This should be breadth first search. And if B is 2, this ratio is 3. That means I'm going to spend 3 times more time. But B is equal to 2 is not that difficult a problem. It's a tree really. I mean, it's, or not tree, but it's only 2. So as your B increases, this number becomes closer and closer to 1. Of course, your problem also becomes more and more difficult. So for more difficult problems, the overhead that iterative deepening depth first search has on top of breadth first search is really low. And intuitively, why is that happening? Intuitively.
Because the number of nodes is increasing exponentially.
Jen, right? Kim.
There's, if B is huge, there's so many more great-grandchildren than there are previous generations.
Precisely. So everything is dominated by this really the last layer. So the overhead is really low. Is it complete?
Yes.
How many of you feel it is not complete? Time complexity we just discussed. Space complexity is B times D, precisely. Pretty awesome. Is it optimal? cost is 1. Exactly. Is it systematic? Just out of fun. Of course not. Yeah, and you can modify this. So in the same way as we do uniform cost search, we can do iterative lengthening. So basically increase your length bound, and then do deepening search. Question, Abhishek.
I think the book mentioned like if you do iterative lengthening, it doesn't come, it becomes worse or something. It's not that good.
Okay.
Can you give some intuition? Like
No, so I don't. I haven't thought too much about it, but I can check. I'll let you know. Book doesn't give you any intuition?
Not much, couple of lines.
I'll definitely have a look. Alright, so this is the summary of what we have accomplished so far. And this is breadth first search, B to the D, B to the D, this is uniform cost search, B to the C over E, B to the C over E, depth first search, B to the M, B, M, depth limited search, which is not useful because it's not complete, iterative deepening, B to the D, and B D. So, that's the
D is.
depth of the solution, the lowest depth of the solution.
Which is M, right?
No, M is the depth of the search tree.
Oh, sorry.
Alright. A quick detour into talking about repeated nodes, and I think then we'll take a short break. So, let's do breadth first search on it. How will we go? A, B, G, and when we find G, we don't have to go much further. If we do depth first search, what we may end up doing? A, B, C, D, G. If we do iterative deepening search, what will we do? A, B, G. Right? Because we are exploring everything till depth 1. So this and this both get explored. And so that's where we find the goal. So interestingly, iterative deepening depth first search expands less nodes than depth first search in this particular example. Now, let's make our life miserable by saying that all of these are undirected edges. Now tell me, what does breadth first search do? A, BG, right? What does iterative deepening depth first search do? A, ABG. What does depth first search do? Good. So here it's a clear demonstration that if you have cycles, then depth first search can have even more trouble. And of course everything else will also have some trouble. It's not that others will not have trouble because you will be repeating nodes again and again and again. What can we do about it? What should we do about it?
Keep track.
Kim.
Have some sort of cache of, hey, I saw you before, I need to come back to you.
Exactly. If we start having that, then what is our space complexity?
E to the
At
M.
least the number of nodes.
B to the D, or depending upon the algorithm. Yeah, whatever.
The number of nodes you're seeing.
Number of nodes here. Now that is troublesome, right? What do we do about it? Yeah, Kim again.
Are we allowed to burn parts of the graph out and say, this just leads to trouble, kill it? You know?
Yeah, I don't know what does that mean. Tell me in more formal terms.
If you've gone from, if you've gone over an edge once, erase it from your edge list.
You don't have an edge list, you have a simulator that is giving you successes. Yes. What's your name?
Chris,
Chris.
I was thinking like we could paint the node or set a property in that we've already visited it or we're currently visiting and then not examine it if we see it again.
But do we store that forever, this information?
I guess we'd set it on the node if it wouldn't work on an iterative.
We don't have an explicit graph, we are generating graph. on the fly. Right. So I mean, you can also all see there's a problem. What's in it?
Oh, Mike,
Right.
if it's like, if you keep a cache of nodes, you can just ditch things from the cache.
Yeah. So you can do,
It's a cache.
Yeah, exactly. Yeah.
Yeah, so you can just compare it to the nodes you currently have in your path. So you just make sure that you're not looping around, but you don't have to store everything.
Great. So you see the spectrum of ideas, and this is pretty much what I had to say. So there's no right answer here, but the answer says, so the points are, A, repeated expansions is an issue. It's a bigger issue for DFS, but it's an issue everywhere. Space becomes exponential if you remember all the nodes. The only one point that you guys did not mention, which is also a subtle point, an important point, is that there is some time that you have to spend in duplicate checking. See, imagine how things are happening. There is a node that, and then you give this node to this program, it spits out successors. So successor would be some state saying 3, 4, 5, 1, A, gap, something like that. Now, even if you are maintaining a cache, you have to go and check whether I have seen this before. It's not like there's node 125 and that is node 125 and you can easily check. So you have to hash this somewhere, or you have to do a linear search or some kind of a search, which is also time consuming. So that's actually an important point. Just the duplicate checking part can be time consuming, right? So I don't know why I've written exponential. Anyway, partial reduction is the solution typically used. And so there you can say, okay, I'm at least not going to expand the same node that I came from. So if it's AB, I'm just not going to expand my parent. That's the obvious first thing. But the better solution is what Zan suggested, which is make sure that you do not expand your ancestor. You do not go to your ancestor again. So you're maintaining this path in depth first search, you are at a certain point, make sure that you're not going to re-expand just this path. And that's sort of the middle path, middle solution. And that sort of mostly works out. The only last point I want to make before we take a quick break is that for now I have been telling you start from the start state, try to reach the goal. There is an alternative solution, which is and try to reach the start state. And just convert the arrows of each edge if these edges are directional.
Or you can go.
Wait. Yeah, you guys are running ahead of me. Samir, what's your name? Andrew. Okay, I'm not going to remember this, by the way, because you just changed your seats, so it just doesn't work. You have to sit exactly where you were sitting last time. So, it's called bidirectional search. You start from the start state, you start expanding. You start from the goal state, you start expanding. And you stop when you meet. The searches meet. Two important points as to when we can and cannot apply bidirectional search. The way I originally defined the problem, I claim that we cannot apply bidirectional search unless there are other additional characteristics of the domain. So what might those characteristics be? Yes, you heard one. Alan.
Only having one goal.
If you only have one goal. Because if you have 1,000 goals, then starting back from all of them is a bad idea.
If the end goal is a state and not a test.
Yeah, it's same. The other thing is that you should be able to invert the edges. So you should be able to get to the predecessors. So yeah, that's an easy, obvious point, and this is an important point. So if you have one or two, or just a handful of goal states, you might still be able to do it. But if you have many of them, obviously you can't. It is complete. The time complexity. This is interesting. So let's just do breadth first search. So general breadth first search was B to the D. Now, how about bidirectional search? If I'm doing breadth first search from both sides, where am I going to meet? So my time complexity of this search is B to the D over 2 plus B to the D over 2 is 2B D over 2. And that's the same for space complexity. I guess it's optimal for the same reason.
So, one question.
Yes.
Sorry. So, about the point that he was making, what if your state
don't have your end state, you just have a test that's.
Yeah, so you can't,
Obviously, in that case, you
you
can't.
can't, you can't.
So-
Yes,
Regarding the completeness, what if the goal does not exist? So for example, I think in the 8 puzzle, there are certain states from which if you start, you can't reach the final state.
Yeah, yeah.
So let's say
They will never meet,
They will never meet.
but you'll expand the whole search space twice. So it's just 2 times bad, and at some point you will not expand any new state.
And you compare the frontiers each time?
Yeah, exactly. No, yes. Yes.
So how do you define meet?
No, you're right. Yes, you compare the frontiers each time. Because it is not possible that this state is same as this state. And the reason is that you would have already seen this state. So you are always going to meet in the frontier. So that is not a very coherent explanation, but yes, frontier.
Then,
Krishna.
sure. So if you go back to the complexity, the time would be, you also have to add the overhead cost for comparing that
compare it.
to,
Yes,
right?
that's a
Which
good
just
point.
might be n or whatever.
Yeah. Good point. Number of node expansions is. So let's see what is the time of comparison. So I have to do b to the d over 2 square comparisons.
No, you can use a hash table.
Yeah, so you'll have to do some clever implementation of it. It may or may not always work. Good point. I learned something.
Yeah, it's like you only have to keep one of the frontiers. You only keep one of the frontiers and you check.
And then you keep checking the other one. But still you have to check so many. So I don't think that changes anything. So okay, so here's what I'm gonna stop at. So this is how breadth first search goes. If I want to start from here, then I will first expand depth 1, then expand depth 3, then 2, then expand depth 3, expand depth 4 based on the graph. This is how uniform cost search goes. You start with a certain length and then you keep increasing your length, you keep increasing your cost, and at some point more and more nodes keep coming into the gap, visually speaking. Now if I want to reach here, what am I doing wrong?
You're
Yes.
expanding in all directions and not just towards your target.
Exactly. So I'm starting from the start state, I am slowly expanding so that I visit the states closer to me first. But I'm completely oblivious to where I have to reach. That is not true for bidirectional, but for other searches. Yes, Andrew.
But at this point, we'd be introducing a heuristic.
Yeah, wait. Of course. Yeah, obviously. So what we are missing is that we don't have a direction in life. We're expanding, looking in all directions. So what we are going to do next after 5 minutes is that we will add guidance, also called heuristic search. Take 5.